Let's do an antiderivative. At this point, we don't have many techniques for antiderivatives. We've just begun our study of this topic. And so when we look at this particular problem and we see the elongated s and we see the dx, that just tells us to find the most general antiderivative of this particular function here with respect to x. But since our techniques are limited, we certainly need to work on making this a little bit more simple. What do we have right now? We've got the power rule for antiderivatives, and we have the basic antiderivatives for the trig functions by working them backwards. So what we're going to do is use the denominator as the clue. X plus 1 quantity squared is the perfect square, and we almost have that in the numerator. So one way to work this problem is just to add and subtract 1. Now when we add 1 here, we get the perfect square, x plus 1 quantity squared. And so now you can see with our nice algebra here, we can divide by x plus 1 quantity squared and get a 1 minus 1 over x plus 1 quantity squared. But of course we can write that with the negative 2 power. Now we're ready for the power rule. For instance, here the x plus 1 is no issue. The derivative of x plus 1 with respect to x is just 1, so that's not a problem with the chain rule. And of course, when we anti-differentiate with respect to x, the number 1, we just get x. That's a special case. So when we move to this part of the problem, again, add 1, divide by the new power. Add 1 to negative 2, you get negative 1. Divide by negative 1 gives us this. And of course, the antiderivative of 1 being x, and then we add an arbitrary constant. And for this part of the problem, I've just labeled it as C1. Now we can reduce this. The two negatives will just give us a positive. So we have x plus 1 over x plus 1 plus the arbitrary constant C1. Now, the one thing that I want to do to make a really important point here is I want to relabel our arbitrary constant. I'm just going to write it as negative 1 plus another arbitrary constant C. The reason that I'm doing this is to make a very important point. Functions having the same derivative must differ by a constant. That's really a result that's due to the mean value theorem, and we've talked about that earlier in the class. It probably didn't have much weight for you at the time because we didn't say much more about it. But now what we can see, if we utilize that result, subtracting the 1 here, getting a common denominator, will just push a minus quantity x plus 1 into the numerator. And then, of course, the x plus 1 here and the minus quantity x plus 1 absorbs. And we're left with x squared divided by x plus 1 plus a c. So often what you will do or find when you have antiderivatives is that maybe yours doesn't look quite like another antiderivative, which is told to be equivalent. And what you would have to verify is to make sure that your answer and the other answer differed by a constant. Because again, when you take derivatives in this particular case, constants just differentiate to 0. So that makes it very puzzling at first, but never worry, when you need an antiderivative, this will work and also this will work. So it's your choice. And we are done.